Now we'll look at scattering off of a repulsive square well barrier, and we could work this problem uh, exactly the way we did before. Remember, we found this rather long and involved calculation uh, when scattering off of a attractive potential well. Uh, and now we'd like to look at scattering off of a repulsive barrier. There's really two cases to consider here, and I'm only going to do one, which is the one that's of most interest. And I could have, remember, we're firing a particle in from infinity, and so it has a given incident energy beam in this incident wave that's being fired in. And I could have this energy greater than V naught, and I could have the energy less than V naught. Classically, the one that I think is most interesting is when the incident energy beam is less than V naught, and so that's the one we'll look at here. Classically, if E is less than V naught, it just comes in here. Here's the energy of E naught less than the top of the well. The particle just hits the barrier and bounces back, so it never gets into the region x greater than 0, and certainly doesn't get over here for x on the other side of the barrier. It doesn't have enough energy to scale the barrier to get over there. Quantum mechanically, we'll see it's a different story. Uh, Now again, we could set things up exactly as we did for the case of the attractive potential barrier and just use this potential and work things through again. It's another long sort of detailed algebraic solution, and we would get the formula for the transmission coefficient in that case as well. But there's an easier way, and the easier way is just to note that this equation holds for V naught positive, but what if I let V naught go to minus V naught? Well, then this thing flips over on top, and so I should get the same results by simply letting V naught go to minus V naught in this solution up here for the transmission, the expression for the up there. And so I'll do that. I'll plug in everywhere in this equation. I'll plug in minus V naught every time there's a V naught. So I get a minus V naught, but it's squared here, so that doesn't make any difference. I've got a V naught here, but that becomes a minus V naught over E. And then here, likewise, I've got a minus V naught. So there's the expression. I need to be a little bit careful here because E is less than V naught. So this number here, since E is smaller than V naught, E smaller than the top of the potential barrier, then this number is negative, and so I should explicitly display that. And so I factor out a minus 1, and now then everything here numerical wise, m is positive, h bar squared is positive, V naught is bigger than E, and so this term is positive, but now I've got this negative sign. And from there, one can take the square root. The square root of a positive number is just this, but the square root of minus 1 is just the imaginary number I. So what I need to do is for this expression here, write it in this form. And if you look at that, I'm going to have a sine squared, or one of the terms would be a sine of an imaginary I square root times W inside there. And I need to remember the relationship for the sign of an imaginary argument, which I never do, but I can know how to get to it pretty quick. A sine of an argument is e to the I of the argument minus e to the minus I of its argument over 2I. That's the definition of sine. And we do that for real numbers or imaginary numbers. We take the same definition. I times I is minus, so I get a minus theta here. I times minus I here is positive. And I can factor out a minus sign to get this in first, and minus e to the minus theta. And it's divided by 2I. And minus 2I here. And I can factor out the 2I, or factor out the I should say, so 1 over I. And then I've got e to the theta minus e to the minus theta over 2. Well, that's nothing more than the hyperbolic sine, or the sinh of theta. And I've got a 1 over I, but if I multiply top and bottom by I, that'll flip it over and I get this. And so if you don't remember it, the sine of I theta is just I times the sinh of theta, or the hyperbolic sine of theta. Well, we can use that up here. Because one of these sines is going to be I times the switch. Okay? And when I square it, I'll get a minus sign. So I get the minus sign out front. V naught goes to minus V naught, so those terms are okay. And then what's inside here is just the sine of this argument, and becoming a hyperbolic sine. And so I get a similar looking expression. If you want the transmission coefficient, take the inverse of this. But instead of a sine, we've got a hyperbolic sine. There's some switches in the variables to make the arguments positive here. And I get some differences in sign for this transmission coefficient. You might notice that as V naught goes to 0, the barrier height goes to 0, so the barrier vanishes, then all of this turns into 0 by virtue of this. And so again, t goes to 1, and all the wave gets transmitted because the barrier disappears. The other thing maybe to note on it is that there is a possibility of you might look at this in some detail. When does this expression here equal to 1, so that the transmission coefficient would become very large? You can take a look at that, but it doesn't produce any particular difficulties, and that's not a very interesting case usually anyway. What else did I say here? Oh, well, this expression everybody should see derived once, and so now you've got it. There's various approximations that people make for this hyperbolic sine, so you may see this in approximate form. But essentially it says that one can get tunneling, transmission, through these barriers, even though classically the particle beam doesn't have enough energy to get through it. And I said it early on that this is of some engineering significance. Well, this tunneling transmission is the basis of tunneling electron microscopes. So they look at how many electrons can tunnel through, and they get information about the potentials. Ordinarily, you can measure this, the transmission coefficient. And if you know the energy of the beam, then you get some details about the potential and maybe the size of the things that you're scattering off of. In addition, there are transistors that are based on this tunneling process, and essentially a large swath of our modern day electronics wouldn't function, certainly not as they do, without this quantum tunneling through barriers that classically they would never be able to get through. Uh, well, I would say work through the details of this calculation carefully. You may need to pause these videos, but go through, check everything, and make sure you understand the steps because it's a like I say, a fairly significant result, and one that if you ever take a solid state device course, well, they'll probably just say, well, remember tunneling, and this was the expression, you know, and throw it up, and then go marching boldly on. Uh, and now you can say, well, yeah, I remember it. Not only that, we derived it in our at-home quantum mechanics course.